Hello, good morning, everyone. First, I'd just like to say a happy new year. I think today is probably the last day of the year that you can say it, but welcome back to the EDIAQI webinar series. As always, let's begin with a little bit of housekeeping. So audio and video settings, please turn off your camera and mute your microphone. The webinar is being recorded. So if you don't want to be recorded, please do not turn on your camera or your microphone. The presentations used will be shared after the event has finished. And please do use the chat box at any time to ask a question. We'll start creating a reserved list of questions to ask our high caliber panelists after. And captions are available. Kindly click on more and then language and speech, where you'll find an option to turn on live captions. So, the promise and perils of AI-driven sensor calibration and smart ventilation. AI-driven calibration is increasingly viewed as a way to improve accuracy of affordable sensors, mitigate challenges such as environmental interference and sensor drift, and reduce dependence on costly reference equipment. By enhancing data quality, these approaches have the potential to move indoor air quality management beyond simple measurement towards prediction and more informed data-driven responses. At the same time, many of these familiar risks associated with AI also apply in this domain. Models may perform well under controlled conditions, yet fail in complex real-world indoor environments. Variability between sensors further constrains scalability, while ethical and trust concerns arise where air quality data, such as CO2 concentrations, may act as proxies for occupancy. In sensitive contexts, including healthcare settings, failures or misuse of AI-driven calibration and automated building responses could, under the definitions of the EU AI Act, potentially be considered high risk. Against this backdrop, the NextAire and EDIAQI projects convened the latest episode of the EDIAQI webinar series to explore what promises does AI-driven sensor calibration hold for indoor air quality monitoring and building management. What technical and ethical and regulatory risks must be addressed to ensure reliable and trustworthy deployment? How can transparent, well-governed calibration approaches support more informed, data-driven decisions in real-world indoor environments? And so with that, we begin our latest episode of the EDIAQI webinar series. And joining us today for this timely discussion, I'm proud and honored to introduce our outstanding panel for today's latest installment. Starting from the left, we have Dr. Tarek Hussain, a professor at the University of Helsinki. Then we have Ms. Maria Figols, Chief Scientific Officer at Imbiot. Then we have Mr. Valentino Petric, Senior Data Scientist at SmartSense. And finally, Dr. Jorgo Preden, CEO of Tinect. So just a quick run through of the agenda. We had the welcome and introduction. We've already done it. We're going to be heading to machine learning and AI-assisted calibration and prediction in the applications of air quality monitoring with Professor Hussain. Then we'll take a look at from sensors to signals, the practical promises and limits of AI-driven calibration with Maria. From there, we'll go from EDIAQI to NextAire, ML recalibration, drift, and health-relevant air quality insights with Valentino. And then finally, we'll go from evidence to trust, scientific validation of AI-supported EDIAQI calibration with Jorgo. We'll have our panel discussion and then questions from the audience. Again, please ask questions at any time. We'd love to create a bank of questions to ask all of our high caliber panelists today. So with that, I'm going to give the floor to Tarek. Please, Tarek, take it away. The floor is yours.
Thank you very much. I'm ready. Next slide, please. So today I welcome you all to listen to my talk, Machine Learning and Artificial Intelligence Assisted Calibration and Prediction in the Applications of Air Quality Monitoring. Next slide, please. We all have the problem and the question how to quantify air pollution exposure and how to get that correctly. We start with the traditional methods, which is combining state-of-the-art setup of measurement networks or the typical monitoring stations network, or sometimes we go a little bit with the cheaper options like medium cost instruments and extensive measurement campaigns. But the problem comes with these stations that they are not covering good spatial resolution, and they do have high time resolution, but they are expensive to use and laborious to maintain. What brings then is the option of low-cost sensors because they are light and easy and cheaper, so we can deploy them in many numbers, but they lack for the good accuracy. Also, they are providing good spatial temporal resolution, and to some extent they can be with high time resolution. So next slide, please. We need to see how we deploy these sensors in an environment and then combine these sensors as a sub-network with the already existing state-of-the-art monitoring network for air quality and try to get a good calibration for these sensors because they, as I said, they lack of the accuracy and they might drift, and we have to calibrate them in the field. We cannot bring back all these sensors in the laboratory and calibrate them one by one. So the calibration should be in a clever and seamless way in the field. Next slide, please. The calibration can be, or the calibrated signal of these sensors can be utilized later in model simulation as data input, or it can be used as a proxy concept that we can extend the capability of these low-cost sensors that they can measure virtual components instead of only relying on the physical components they are measuring. Next slide, please. So the framework, how to do it. First, we need to look at this as three main phases. The first phase, which is the monitoring and sensing, and we look at deploying these sensors in different environments, either outdoors or indoors, or carry on with people to quantify the personal exposure. And all these sensors require to send the data, which is going to be combined with other available data from the state-of-the-art or medium-cost instruments, or building a comprehensive database of air quality, whichever the method or technique is coming. But of course, we have the reference as the state-of-the-art measurement stations or reference instruments to get our calibration correctly. Then we get the raw data accumulated in a way accessible for the next step and pre-processing. And for this, we need to use machine learning and artificial intelligence before we do the calibration, because sometimes we need to fill in the gaps and check the quality of the data. If we have huge data, it's not possible to do it manually. So we have to run some kind of automated methods using machine learning and implement artificial intelligence to correct the data or to do some gap filling in the data and get this processed data in a way harmonized as well to get it ready for the next step, which is calibration. So please, next phase. So this comprehensive environmental data, which is corrected, is ready to be used with our applications for the indoor air exposure or outdoor air exposure, or even investigating the spatial and temporal variation of the air quality. How we do this depends on the situation, of course, and the needs. So next slide, please. And how we can look at it is kind of boosting the sensor capabilities. Next slide. So if we think about a low-cost sensor and we would like to boost its capability, either to get it in a better way as better accuracy, or to boost its capability to go beyond the physical monitored parameters, to give us, for example, black carbon, which is not measured with a low-cost sensor, or lung deposition surface area, which is another parameter important for the health effects, and it's not measured directly by a low-cost sensors. Usually, these parameters are measured with expensive instruments. So we think about the database and then pre-training the data. For example, the sensor data should be trained against the reference instrument data, and then deriving the so-called proxy or the mathematical equation that is capable of getting the sensor as imitating the reference instrument. We have two options here, either a black box model or a white box model. For us, it's easier to use the black box model. It's highly accurate, but sometimes we try to see supervised machine learning and artificial intelligence to look at the equation directly and try to interpret the results. Next slide, please. So here I show one example of boosting one measurement to get the lung deposition surface area and deriving this proxy from other parameters, for example, PM 2.5 and size distribution, or maybe number concentration. If a sensor has the capability to measure PM 2.5 or NOx or any other parameters included in the training, then this proxy is working to get an estimate for the black carbon from the direct measurement of the sensor as virtual sensor. And the sensor itself is calibrated by machine learning so that we make sure it is giving a proper PM 2.5, because if the PM 2.5 or other parameters measured physically is not calibrated, then this estimation or this boost is not possible. Next slide, please. Here is an example of black carbon from real situation, and you see we have so many parameters measured in at a reference station or the state-of-the-art station, but we know that our low-cost sensors will measure one or two parameters, and these parameters are going to be used as input in this proxy. First to be calibrated and then to estimate other parameters imitating the reference station in the air quality measurement. Next slide, please. And this shows how powerful was the machine learning and the artificial intelligence in predicting black carbon using the proxy from a low-cost instrument. Next slide, please. Thank you.
Thank you very much, Professor Hussain, Dr. Tarek, for that really deep dive into low-cost sensors and the potential of AI calibration. Interesting. I actually hadn't known that a really big benefit, I guess, is that you can do the calibration in the field rather than needing to take it back to the laboratory, which is very interesting to hear that, actually. Now we'll go and turn to Maria. So we saw from the academic side. Now we're heading to the private sector. Please, Maria, take it away. The floor is.
Thank you very much. Thank you, Alex, and thank you for this invitation. Yeah, today I'd like to share our perspective as manufacturers on what AI-driven calibration can actually offer for indoor quality monitoring. And of course, I will speak from this private point of view, from a device manufacturer and not a sensor manufacturer, which is slightly different. And of course, we are working with real indoor environments. Next, please. The main idea of this talk, mainly I think would be from the whole webinar, is that measuring is not going to be enough. What matters now is how sensor data signals are going to become reliable, interpretable, and in our case, mainly usable for decision making. So next, please. AI has clearly entered this conversation around calibration because of its promise. Its promise to handle non-linear sensor behavior, like now it was explained right now before. So to help, it also promises to help address drift and aging effects, and also to scale calibration approaches to a large sensor networks. However, as we can see, or as I see, the reality of real deployment in indoor environments can be more complex. Models are often strongly context dependent. The performance can even degrade over time, and the internal behavior is not always transparent or at least easy to explain. So this tension between promise and reality leads us to a very key message from our side, is that AI can only be meaningful if it is built on strong validation practices and of course, clear data quality foundation. Next, please. So indoor environments make this issue particularly difficult, or at least challenging. Unlike lab conditions, indoor spaces are dynamic or heterogeneous, or highly contextual, because occupant behavior changes continuously, ventilation strategy changes, activities introduce episodic events, and even the same room conditions can differ significantly. So as a result, calibration cannot be treated as a one-time action. For us, it is an ongoing process because the environment interacting with the sensor is constantly changing. So next, please. This leads to an important clarification, at least from our side and from the private sector side, is what do we actually mean by calibration? In practice, calibration is not a single step. It involves 3 complementary layers. First, device level adjustment, which guarantees basic sensor functionality and consistency. Second, environmental compensation, where contextual effects such as temperature and humidity are accounted for. And third, performance assurance over time, which addresses drift, aging, and long-term stability of the sensors. So understanding calibration as a process rather than an event is essential before discussing AI in this context. So next, please. So once calibration is seen as a process, the basic step is validation. So reliable indoor quality data requires end-to-end validation across the entire device life cycle. So from manufacturing quality control to deployment checks to operational corrections, and of course, finally, to fleet level currents. From our perspective, this is a fundamental principle, and validation must come before intelligence is applied. So AI can enhance, of course, all these processes, but it should never replace the foundational work that ensures data behaves in a consistent and current way to what it is expected in indoor environments. Next, please. So what does this AI-based calibration actually imply in practice? Tarek explained very well this scientific background of how to treat low-cost sensors. And we actually need to move all this knowledge and apply all that knowledge into practice, into real manufacturing practice. And that typically involves multivariate data-driven models that are going to relate the sensor signal to contextual variables. So mainly, again, temperature, humidity, and of course, temporal patterns that we need to identify in indoor environments. So these models can improve performance under complex conditions, but at some point they're time dependent. So their effectiveness can degrade, sometimes without even knowing, can degrade silently, which means continuous supervision is essential. So in other words, AI increases flexibility in all these processes, but it still needs, or might even increase the need for oversight. It's not a one-time action, it's a continuous process. So next, please. At this point, it becomes clear that calibration alone is not enough. For us, instead of asking if this sensor is calibrated, for us, it's a more meaningful question to just point out under which conditions can this data be trusted and for what purpose. And that is going to help us define the environment to understand all this variability in the indoor environment. So this is where the concept of data quality levels comes in. A data quality level approach frames calibration within a broader structure, a broader governance structure that makes data reliability limitations and intended use more explicit. So in practice, data quality levels shift the focus from just producing numbers to actually producing data that is fit for a defined use case. So all these converting data into useful information makes a lot more sense here when we are, and as manufacturers, we just not only pretend to show data, but to actually use this data to take action, to improve in their environment, to control or an BMS system or ventilation system. So we actually need to focus on this data quality level as part of the whole process. So, and also it is very important to also keep a human in the loop here. It is, and especially in indoor environments assessment and control, where all these changes actually we need to continuously understand all the background from this human perspective and giving all the algorithms and all the AI applied all this human perspective. So next, please. For us, as a device manufacturer and also system integrator, all of these translate into what we can call a data quality program, which is built progressively. It starts with, of course, hardware and integration quality, which is going to help us ensure that the integrated device behaves consistently as expected. And then it continues with device level validation and adjustment, and that includes screening and environmental compensation. And once devices are deployed, it also extends to operational and fleet level data quality, as explained before, where currents and drift and anomalies can be monitored over time to actually be able to treat them. So only after all these layers are in place, it makes sense to talk about AI-supported pattern analysis and monitoring. And here the key idea from our side is that AI does not define data quality, it operates on top of it. So that's where we are. I mean, understanding and defining and checking all these processes to actually implement all this AI layer above all of that to be able to continuously improve all that process. So next, please. Once data is explicitly defined and maintained, that's when we can move beyond calibration into higher level applications. In this case, I want to show you just a very quick example of CO2 forecasting in schools as an interesting starting point. And this work, which is the starting or the basic of the PhD work from one of our colleagues, and this work validated monitoring data is used to train time series model that is going to predict future CO2 levels. Of course, this is forecasting. This is not calibration. We are not adjusting yet the sensor, but all we want to is anticipate future conditions. And next, please. Here the results and the point of this study is how these simpler models that also were pointed out before by Tarek, but can be enough for very, very short horizons in time, while more advanced models are going to add more value for longer prediction horizons. And why is this important? Why is this so interesting? Because it's going to support these proactive ventilation strategies without requiring infrastructure changes. That means, and that has a major impact in the economic of the building, and that is also part of the balance. So it's going to help us illustrate how, of course, at this stage or next steps, how AI can add value when it's based on trusted data. So first, we're going to validate data. We're going to test. We're going to see what could be the next step. And in this case, the next step of this project, of this work, would be applying all these methodologies for different scenarios and not only schools, which is also interesting to be able to apply it for indoor environments, and actually be able to trust data for next projects. So next, please, to conclude, of course, AI clearly plays a very important role in indoor air quality monitoring from manufacturer point of view, of course. But right now, as I see it, the value does not come from replacing calibration or replacing the validation. It comes from being embedded with this strong data quality program, and of course with transparent governance and of course the human expertise that we're going to see here today. So the future is not autonomous AI driven calibration, but AI supported data quality and decision making. So thank you very much, and yeah, happy to listen and learn, of course, from next steps. And yeah, thanks Alex for sharing our LinkedIn page, and you can follow us. There's the information in the chat and here to listen and answer any questions if they arise. Thank you very much.
Thank you very much, Maria, for that very comprehensive and concise. You did perfectly in the time. I might add that you had allotted, which is always very, very welcome. Very important points. Environment has so many different variables, right, that it's very difficult to kind of mimic those variables in a lab setting. For example, silent degradation. This is, I think, a really interesting point and something I definitely want to do a little bit more research on. And I think obviously we tried to hint at that as well as the concept note is sort of this proactive cost-saving measures that come with AI calibration. So thank you for that look at the private sector and at some very interesting work happening at InBio. We stay with the private sector now and actually a European project at the same time, heading to Valentino Petric, PhD candidate, to talk about his work at NextAire and also the company SmartSense. So please, Valentino, take it away. The floor is yours.
Talk today about EDIAQI and how what we learned from EDIAQI and how we plan to move this to the NextAire project through the paper we have recently published. You can go out to the next slide. Yeah, as Alex already mentioned, I work at SmartSense. I'm data scientist there, and you can go again. Yeah, as I said, EDIAQI to the NextAire project through the paper we have published on machine learning recalibration in the project of Zagreb. So first of all, air pollution as a public health risk. Why is it important? In this recent research we did, we focused on particle matter and NO2, which is linked to respiratory and cardiovascular diseases, but it's affecting us in every part of our lives. But yeah, particle matter is especially important. The lower we go with the particle size of PM2.5, PM1, it will impact us in a deeper way. It will go into our bloodstreams, and I found even a paper that stated that it will go in our nervous systems, in our brains. Urban exposure is rising. Here in Zagreb especially, we recently had increase in traffic, and it's affecting every part of the life, I think, from working, living, and things like that. And as Tariq stated, we need high resolution monitoring to give any kind of public health risk assessment. We need it because we want to have a network around the city which is reliable enough so we can draw conclusions, because reference monitoring stations are expensive and not always and cannot always be applied in the field at every part of the city, with cities being big, with sources being, as I put it on this graphic, sources can be different from factories, vehicles, construction, dust. Zagreb, in our case, is rapidly expanding, burning fuels from domestic heating during the winters through the fires we have. We recently had near Zagreb one where rubber storage was burning, and or tire storage to be exact, and skyscraper was burning recently. So yeah, that was unexpected, but still we had sensors network that could detect it. They all produce harmful pollutants that affect us in, as I already said, respiratory system, cardiovascular being the main ones. It's connected to the cancer and even some brain damage. If we go to the next slide, please. So why we come from EDIAQI to the NextAire, and what we basically in different projects, but we learn a lot from EDIAQI, and we will move it to the NextAire. EDIAQI was focused on mostly on normal, or I think we solely on indoor air pollution. We assessed exposure routes and health risk in households, in public places such as shopping malls, schools, kindergartens. We used sensor networks, mostly local sensors in that project, and I think we have managed to draw some policy and public engagement to it. And we will continue to do these things in NextAire, where we will focus on EDIAQI and sensors through development of talent. Next researchers, we will share our knowledge, expand on the things we have already learned, and we will learn. We will use different air quality systems. We won't only focus on indoor, we will focus also on outdoor, and try to connect air quality to the public health application in some ways. Next slide. So we come to our study we recently did. So it was in Zagreb. Here you can see the map of Zagreb with a reference station and our indicative measuring station, one being the red pins on the map. You can see how big of an area we can cover with indicative measuring stations compared to the reference station. We had 35 of them with 4 reference stations. In this paper, we have focused on, as I already stated, particle matter and NO2. And we use XGBoost for calibration. And on these 2 pictures in the bottom left, you can see why indicative measuring stations are easier to install than reference stations. On the left is on our main square in Zagreb, our measuring station, and on the right is the blue pin in the middle of the city. It's a reference monitoring station. It needs a lot more infrastructure than our measuring station. Next slide, please. Why is it important to recalibrate the sensors in a health assessment way? Because we require accuracy and precise measurements, but these sensors degrade over time. They drift in bias, and as you can see in this figure, you can see if we focus on hourly frequencies, the absolute error is much larger than when going through daily and even weekly resampling. But if we draw some kind of health assessment conclusion, we need this error to be as little as possible or no error, which is hard to achieve, but we strive for it. Next slide, please. And then we come to our pipeline we have developed. So we have used our smart sensors indicative measurement stations, data from hydrometeorological institutes, also for reference stations.
So you're breathing them constantly.
And we have employed the satellite data from Copernicus ERA 5 satellite, which has the resolution of 0.5 times 0.5 degrees. We have all put that through our data processing pipeline, where we did all the necessary steps like cleaning the data, outliers, filtering or adding features such as time, which we want our model to be seasonal. We have done that using different techniques, implementing is it a day of the week, month, day of the year, holiday. We have also developed a traffic proxy since we didn't have traffic data, which is important for these 2 pollutants we have focused, doing a polynomial function that will simulate the rush hours of each station. And then we have also here put an OpenStreetMap, some sort of classification algorithm that will connect the reference station to our measuring stations in a way that will assess the area around the station and pick the station which is most close to the reference one, meaning it will have the most percentage or similar percentage of roads. Is it a main street? Is it not? Does it have some sort of foresty area, some sort of grass around it? And we have managed to correct nonlinear bias and reduce measuring error in all our tests. And after we have trained the model, we have deployed it, and we are focusing on drift monitoring. Next slide, please. As I said, we have managed to reduce an error up to 82% on one station. You can see on the blue dots, we have improved all the measurements. On the left column is NO2, and on the right is particle matter. And you can see that with our approach, we have managed to come up to 82 for NO2, but for PM10, it's around 30% or 41. So yeah, this will improve the model, and you can go to the next slide. And we can deploy it and track drift using a rolling random mean square error. And how we do that? We deploy the model and we see how it will degrade over time. You can see that in some stations it doesn't degrade in our period of I think it was 1 year, if I'm corrected, and some degraded over 1 month, some degraded over 6 months. But using this approach, we can always recalibrate the data and get the best possible results that the sensors can produce, and we can do a good health assessment using our measurements. So this is an operational tool we can use for sensors networks. Next slide, please. Why is all this important? Why we focus on it? Basically, with this kind of network and measurements, we can do a traffic-related hotspots. We can see peaks of particle matter. We can analyze local pollution events. Okay, in close proximity of the station, it's some new construction site, so take care of it, or there's traffic that is maybe some road is rerouted and the traffic will be higher these days, etc. So using this kind of network, we can analyze it and see, okay, wind is blowing in some way, we can expect some kind of pollution, and we can instruct people how to behave and how to take care of their well-being. Next slide, please. Here I have put one slide that showcases our products and how we can utilize them. So we have developed the outdoor air quality monitoring system, which is used in Zagreb. It's a different design than the one you saw in previous photographs. We also focused on indoor air quality. As Maria stated, it's a really important topic and we need to talk about it. And our platform, which are showcased in the last slide, you can analyze your data and see it real time. Next slide, please. That's all from me. You can follow NextAire project using this QR code to see the development we do, how we improve sensors research, and how we share our knowledge. So yeah. Also, here are my social media and SmartSense, so you can follow us there also. Thank you.
Just give firstly a shout out to NextAire. They're taking a lot of the learnings from the EDIAQI project. So I do advise strongly to check it out. Some very interesting work happening there, and some very nice papers that I know that Valentino has already worked on that were very interesting. I will be honest, maybe I understood 5%, but I realize how much more there is to understand from that. I also want to just add, I think, Valentino touched on the health effects, which is a really important thing, using the sensors, the low-cost sensors to understand health effects and to create connections. Seasonal models, I think that's a very important point as well, something that I hadn't reflected on, but maybe you need different models depending on the season. Traffic as a proxy, and I think maybe one of the most shining things is this is a real life example of reducing 82% of error. So I mean that's it's no small number at all. So very interesting look at some of the work at NextAire for smart sense. And now we'll be staying with the private sector, moving from NextAire actually back to EDIAQI. And yeah, take it away, Jurgo. The floor is yours.
Hello, everyone. I'm really pleased to speak here today. And also, I want to thank the previous speakers. I think the background was very well laid out and the technical aspects described. So my talk is going to be more from an operational and applications perspective. We, as a company at Thinect, we have deployed thousands of devices, both sensors and controllers. And we have hundreds of outdoor air quality sensors, and also we have hundreds of indoor climate sensors that we have deployed. And in the context of the EDIAQI project, we deployed over 100 quite complex indoor climate sensors collecting data from indoor environments. So I'm going to look at, as I already said, from the applications perspective, from the operational perspective, because I think the expectation or the desire should be to make air quality information available, trustworthy air quality information available to lots of people, and also then to control the buildings using accurate indoor climate quality data. One of the things that we also do is we control building systems, and you need accurate data to do that. Next slide, please. So challenge to be addressed. So these were already to some extent discussed previously. Historically, indoor climate sensors going beyond just temperature and humidity were specialty products offered in relatively low volumes. And so the installation was quite laborsome, and also the calibration procedures were then acceptable. So this paradigm is changing now that the sensor technology cost has come down, and we can really deploy also more complex indoor air quality sensors in volumes. Then the paradigms are changing, and the large-scale adoption requires also the rethinking of the installation and the calibration workflows, and how we can make these sensor systems, these data collection and information extraction systems reliable and trustworthy. And of course, AI-supported calibration helps us here, and this was discussed in the previous talks of how we can do this AI-aided calibration and data conditioning. Next slide, please. So user expectation, or then let's say expectation from companies who would be deploying such systems, because this is the goal, to have the data available, information available at a large scale. So the devices should be deployable by technicians with no special training. So there shouldn't be any specialized tools or specialized knowledge needed to deploy such devices. And the devices should operate autonomously without interruptions for decades. Maybe several decades is a bit challenging, but the thinking should be that we can put the sensor stations in place, maybe replace something there, or the replacement should be fairly simple, but these should operate autonomously without specialty support or specialty engineering. So this also means that the issues should be detected automatically. So if there is issues with the sensing, or if there's issues with the devices, connectivity, whatever, so these should be detected automatically, and the workflows to correct any detected issues should be streamlined, so that when there is an issue with a sensor, with a calibration maybe, or whatever, that there is streamlined workflows where not highly skilled technicians can correct these, so that we can really have it smooth and cost effective. And also what is important, which oftentimes people forget, is that the information extracted from the data should be available to the users without need for interpretations by specialists or scientists, so that we are not only collecting accurate data, but we are also extracting actionable information to regular users from these data, so that they can make sense of what is happening in the indoor environments and also outdoor environments for the outdoor sensors then. So things should be simple to deploy, simple to service, and also simple to interpret the information extracted from the collected data. Next slide, please. So we have the evidence from the accurate sensing, calibrated sensors. How can we create then trust in the user? So and the system integrators that the systems can be used at a large scale and for a long term. So the evidence-based validation of the sensors creates trust in the sensor data, and then the scientifically proven algorithms create trust in their information extracted from these sensor data. So we must have then the validation and scientific rigor in multiple steps here and in multiple aspects to ensure that the systems are trustworthy. And so the validated and trustworthy data to information chain enables the use of this cost-effective IoT-based information delivery. So we want to have cost-effective sensing, we want to have cost-effective device solution deployment, so that the validated and trustworthy systems would be then used. And this also then enables data to decision workflows, whether these workflows are then maybe where a human is involved, maybe corrections to indoor climate parameters, or correction to the climate maintaining systems in the building, or these workflows could be also automated. So let's say we have an HVAC, heating, ventilation, air conditioning system in the building. So in order to trust the operation of these systems, the underlying data collection, data processing systems need to be trustworthy. So we need to have the evidence there. We need to have scientific rigor, and from there we can build the large-scale systems that can be trusted by the users. Next slide, please. So this was already discussed at quite some detail by the previous speakers also. I'll just go quickly over it. So as I already mentioned, the AI-based tools and algorithms can be applied in multiple stages. In the data assessment, filtering the readings, assessing data coherence, adjusting the data for correctness, calibrating the data. So we can do the analytics, we can do correlation-based analysis, we can apply all kinds of methods, but then we have also the information extractions for users. So there we also want to have tools that can adjust to the change in sensor locations, as well as the data provided by the sensors, so that the information extracted from the sensor data and also the presentation of the information is understandable for the users, and also that the data is then trustworthy for the users. Next slide, please. And of course, so I've talked about the different aspects where that we need to address. So the data collection, processing, calibration, and so on. But in order for the systems really to operate for decades in a way where they are trustworthy, where the users can really use the systems without worrying about the validity of the data or the information, we need to have governance in place, so that we can be sure that how the system was designed, that this is also how it is being implemented and deployed at the sites at the different locations. So this means that the process from deployment to information presentation must be well described and correctly implemented. And also the monitoring methods must be in place to ensure that all the process steps are being followed as described, because only then we can have trustworthy information. Otherwise, even when we have the best devices in the world, we have the best calibration methods, but if the implementation deployment process doesn't follow the prescribed processes, then the data cannot be trusted, and information either. So we must. What I'm saying here is then in addition to designing the systems with scientific rigor and then making sure that all the information is trustworthy, we must also take care of the process part, so that the deployment and the maintenance of these systems follows the the expected steps. And then continuous governance is needed then to ensure the long-term repeatability and trust. So as you all know, trust is difficult to build, but simple to lose. So we must also keep this in mind when building and implementing these systems. And next slide, please. Simple can be harder than complex. So while the AI-based data processing and integration can help us to enable cost-effective large-scale analytics and control solutions, these must be also simple, because when it's too complex to deploy, too complex to maintain, it will not be adopted by the community. So I mean, we have seen this with our solutions and our customers. We have a team of technicians who deploy our solutions and who maintain these. And when the solution is too complex from the deployment part, but also from the user perspective, so understanding data and so on, then it is very difficult to ensure adoption and to have adoption at the large scale. And I believe this was the last slide for me. Thank you.
Jorgo, thank you so much for that kind of deep dive into trust and the issues of trust in terms of sensor calibration. Very much appreciate the point. Trust is, difficult to build, but very easy to lose. I think that's very, very true. And that's a really strong point I think is going to be taken from today, that complex might be easy, right? But simple might be the difficulty, right? And I think that touches a little bit upon, and I really appreciate that. I promise you we did not coordinate for this, but it touches on the next webinar theme, which will look at data visualization and making that very accessible as well. Promise there was no coordination there. Okay, I invite all of our panelists, please, to turn on your screens because we are heading to the panel discussion. And I thank all the panelists because they were very on time today. Only 7 minutes over. I think this is the least amount over we've ever been. So please, Tarek, Maria, and Valentino, if you could turn on your screens. Perfect. Okay. We're going to go classroom style, as always, starting from our first speaker and going to our last speaker. So first, and a big thank you, of course, as well to all of the speakers for their very good. Thank you very much, Jules, for that. It's been really great presentations, super deep dive. And I think without coordination, we went across the whole spectrum of things. So I think that's pretty. Per, if you could ask your question in the chat, and we can actually offer you the floor at the question portion of the discussion, which will be in about 15 minutes. So Tarek, please, first question to you. Which use cases are currently best suited to machine learning and AI-assisted calibration and prediction in indoor air quality monitoring? And let's, of course, extend that to outdoor air as well. So please, Tarek, take it away. The floor is yours.
So as I said in my presentation, it depends on, or it varies from case to case. But basically, machine learning and artificial intelligence have been really very efficient in indoor air quality monitoring as well as outdoor air quality monitoring.
Thank you, Tarek. And so building on that response, Maria, which environmental factors remain most challenging for AI-based calibration methods to handle reliably?
Yeah, many of the most challenging factors are, of course, environmental, and they are also very strongly dependent on the parameter and the sensor type we're using. As explained before, humidity, temperature are always, and also occupancy, ventilations are going to be key to actually understand and define the data to actually be able to have reliable training data. But first, the main challenge is, as I said, not the same for parameters. For example, for PM sensors, especially optical low-pass sensors, as explained, are highly sensitive to relative humidity, so that can very significantly alter particle size and optical response. So this makes humidity one of the most critical aspects in this case. For other sensors, like gas sensors, and mainly electrochemical sensors technology, long-term drift, aging, and cross-sensitivities remain major challenges for just manufacturing and also, of course, for any additional AM model. And in contrast, parameters such as CO2 tend to be more stable from a sensing perspective, but even their indoor dynamics may introduce or may challenge a little bit calibration and validation at some point. So spatial variability plays a very important role here, and two sensors at the same time deployed in the same room may experience different microenvironments that limits a little bit all the models trained under one specific context. So yeah, this is why calibration, and I go back to my point here, it was not a parameter agnostic or sensor agnostic, it has to deal with all these environmental contexts at the same time, and the technological specifications.
It's very interesting because Tarek had touched on that on the real world, and actually everybody's touched on the sort of environmental factors, and it's very interesting to hear you could put a sensor in the same place but get some different. Very interesting to hear that point as well. And humidity is one I feel like I hear very often. Temperature. These are the ones that are very often, especially in the literature as well. Building on that, Valentino. Then why is calibration quality especially critical when sensor data is used for health impact analysis or local event assessment?
As I already stated in my presentation, we want data to be exact, to make some sort of health impact analysis or local event. We want calibration to be good, so sensors can drift over time, they can lose their capabilities. So we need calibration to follow that and to get the as closest to the source or to the exact measurement from our devices to make any kind of assessment or conclusion from it.
Really, there we're saying location is one of the most important factors in some ways, which kind of builds on what Maria said about the spatial dimensions, right, which are like key factors here. Okay, turning to you, Jorgo, building on top of this, where do you see the greatest opportunities and risks in combining AI calibration with large-scale IoT deployments for indoor air quality? There should be management there, actually, but for indoor air quality management in the future.
Thank you. Yeah, so definitely IoT-based calibration and using IoT technology supports the adoption of the indoor air quality monitoring solutions, enabling then also large-scale deployments, talking of hundreds of sensors per building, reducing the human overhead, which reduces cost and enables then the adoption or supports the adoption, because I think until now that one of the main barriers has been the cost for the end users. So indoor air quality is becoming increasingly important as a topic because air pollution is increasing and health aspects are becoming more important. And I think importantly, what most people do not know about is that there is a new directive called the Energy Performance for Buildings Directive in the EU. And this mandates that in buildings where efficiency is improved, also the indoor air quality is monitored. And in order for this air quality monitoring to be reliable, trustworthy, and also easy to adopt, I think it's critical for us, companies like us, and also researchers involved in this area to create the solutions that can be easily deployed at a large scale so that actually the air quality can be monitored in the building. So instead of using some, let's say, cost-effective, obscure sensors that do not provide long-term data and are not long-term reliable, users can then opt for trustworthy calibrated sensors that provide trustworthy data for them. And also then same also for the controls. So people are sometimes worried about the controls part. Can I trust the demand-based ventilation controls? So using this kind of calibrated trustworthy systems, we can also then tell in clear conscience to the users that yes, the controls can be trusted and can be relied upon. And just a quick note. So actually, based on the work we did at EDIAQI, so health threat analysis, we are now planning to start a project also applying this for indoor environmental controls in hospitals. So demand-based ventilation control in hospitals using accurate sensor data. So we are looking at doing a research project also in this area. Thank you.
Super interesting on the last element about the project. I think that really builds on some of the work that Valentino is trying to do at the NextAire project as well. So I think there's some potential for collaboration, at least knowledge sharing on that front. I do want to build on the point about, I think health is becoming, especially the indoor space as well. If you look at, obviously the COVID-19 pandemic had a big impact on that, right? We had a realization again of how important the indoor space is and how the effects of ventilation really have an impact, right? And we had actually the last webinar as well, like having effective ventilation can reduce contagion between people, like significantly. And people often point to the airplanes for that, right? And to the statistics there. And then there was your last point. I'm forgetting it now. I'll probably remember it afterwards. The Energy Performance of Buildings Directive, super important. I just want to highlight, I think that's an opportunity for everybody here, right? And maybe that's an example of regulation actually creating economic opportunities, right? So maybe this breaks against the idea that regulation is somehow a barrier to innovation sometimes, or a barrier. So just maybe to highlight that as a nice example, and an appreciation, Yurko, for mentioning that, because it's something I really believe. Anyhow, sorry. I am the moderator, going back into moderator mode, and I'm going to turn to Tarek here. Where do you see the main limitations of bottlenecks preventing these approaches, AI approaches, from being deployed reliably at scale in real buildings, for example, or in real studies?
Yes, this is a very good point, how these are limited and what are the limitations. If we think about the sensor itself and how it is operated, then we have to make sure that the sensor is operated in the right way. Otherwise, the calibration has no meaning, and all the process is not possible to be relied on. And this comes as a responsibility for the users themselves, how they maintain the sensors and keep them in a good way of operation. For example, some sensors require a certain orientation or a certain setting. If that does not mean, it means the data, even if it is calibrated, it will be wrongly calibrated. So this is one of the limitations to mention, but there are also other.
I think it builds on a lot of the spatial point as well from Maria, kind of before what you mentioned as well with the environmental factors. And it does put like a big responsibility, right, on the users that, and obviously I'm thinking here, if it's a school, for example, the school administration, right, ensuring that it's proper usage so that it actually has the intended impact. For example, reducing school absences, for example, could be one of like an actual real impact, right? But that requires responsible use of it as well. So I like as well the point, because I think Yorgo said that we need to make sure the users trust us, but also the users need to do things as well to ensure that so it's a bit of a two-way street as well. Maybe I might be wrong here, but that's what maybe I read a little bit now from this point as well. Heading to Maria, I'm building on what Dr. Tarek has said. How do you balance calibration accuracy with transparency and explainability at the device level? I know we've touched on this a lot, but maybe for a few more words on that.
Yeah, sure. For us at some point, balancing calibration accuracy with transparency starts by what we've been talking about, is that recognizing that not all sensors technologies behave in the same way in the same environment. So in indoor environment, in indoor quality monitoring, some sensors technologies are better suited to relative measurements rather than absolute ones. And this is the case for very specific sensors, which are MOX sensors used for VOC monitoring. where the values lies less in absolute concentration and more in detecting changes, patterns, and deviation from a baseline. And very similar situation comes with electrochemical sensors. While they're very valuable for specific gases, may have some cross sensitivities to other compounds. So this means that interpreting individual absolute values without context can be misleading. So for these reasons, we place very strong emphasis on precision, on consistency between devices and response to events, peaks, trends, temporal evolutions, rather than just focusing exclusively on absolute accuracy. So at device level, these lead us to prioritize transparent, informed adjustments where behavior can be explained, traced, and validated over time. I mean, we don't want to optimize. I mean, we do not optimize calibration for accuracy alone. We optimize this trustworthy data where the behavior of each sensor technology is going to be well understood and it's going to be consistent across other devices. And here's where we can, or where AI can help us or can support interpretation rather than just hiding sensor limitations. So yeah, coming up with here the precision versus accuracy, which is very interesting debate also for this session, I think.
It's really, I promise you there was no coordination between us beforehand, but it really builds off what Tarek had said, right? That it's also on the user to make sure that it's being implemented in a precise way, in the way that it's meant to be implemented. So I think it really builds on Tarek's point. Promise there was no coordination. Valentino, please, the next floor is yours. The next question is yours. How can NextAire build on EDIAQI's work to ensure that good practices in sensor calibration become a durable standard rather than a project-specific solution? Please, Valentino.
In EDIAQI, we acquire the knowledge about indoor quality and how we can optimize it, make it better using filtration devices, opening and closing the windows, monitoring our stay inside, and things like that. And in NextAire, we will continue with this knowledge built, as Jürgen said, we need some kind of pipeline or some sort of procedure that will make us all use some sort of standard, and all research groups and institutes will help us with that. We have in NextAire great consortium of different people, so even the sensors provider or device providers and academia that is experts in this field. So yeah, I think we need to create some sort of knowledge base and pipeline that researchers and talents use in the future and develop and adopt our research into their projects. And we hope that NextAire will live long after it's finished. Yeah.
I'm sure it will. I think obviously training in this has been a very dominant theme today, is going to become ever the more essential. People are taking much more of a focus on the indoor spaces, Hugo has said. And maybe just to add on the point about the pipeline and knowledge, I can see it already happening that they're creating this pipeline and knowledge. So we'll come and call you again, but please do follow the next project. Okay, for our final question, and then we'll head to all your questions in chat. We have some nice list of questions in the chat now. But before we go there, last question today in the panel. So Jurgo, looking ahead, how can EDIAQI's results help shape future projects that aim to integrate AI calibration, secure IoT architectures, and policy-ready IOQ monitoring? Please take it away.
Thank you. I see there are a bunch of questions also in the chat, so I'll try to keep it short. So the question is about projects, but as I already said, I'm a very practically minded person. So I'm also looking at commercial adoption and widespread adoption in the society, and looking at how the EDIAQI results can help there. So from my perspective, the EDIAQI project shows, or the results of the project show, that cost-effective sensors can be applied in indoor climate monitoring and health risk assessment. So combining the IoT architectures, secure IoT architectures, data processing, and so these can be used both for the people to understand better indoor climate quality, health risks, as well as for controls of building HVAC systems to optimize energy consumption. And so also the EDIAQI results then create a platform to update policies requiring the indoor climate monitoring, because unless there are scientifically proven methods for this accurate monitoring, then you can't create policies demanding that either. And also I think the demand-based ventilation control can be demanded as part of policies, because this greatly enhances energy efficiency. So we have seen, I mean, 10 to 30% energy efficiency improvement in buildings just using demand-based controls. In some rare cases, even 50% energy efficiency improvement. So I think these results are very important and also pave the way for future work in this area. And so both for projects as well as for commercial applications in the society. Thank you.
Thank you for that nice closing of the panel discussion there. And so maybe policy is the root. I think that might be one of the biggest important things, and we need to start building more on the policy side in order to kind of foment. And I think just to underline as well, this sustainability aspect, right? Obviously, that's a really critical aspect.
And just as a quick comment, so I mentioned the hospitals previously. So until now, the HVAC engineers have been really hesitant in applying demand-based ventilation in hospitals because they are worried about the air quality. And unless they have trustworthy, accurate air quality monitoring solutions in place for the hospitals, then they would not use demand-based ventilation. So which then helps the energy efficiency. But when we have these systems, then we can also do it there.
No, it's a very important point. I think obviously hospitals where you have vulnerable populations is one of the, and schools as well, is one of the most, let's say, important, well, not to rank settings, but it's an important setting to consider. Okay, we have a nice list of reserved questions. We have a nice amount of time actually to answer them as well. What's really nice as well is most of them are addressed to all of our panelists, so we can continue with our sort of classroom style building on like that. And I think they're all a very nice list of questions. A big thank you to my friend Sotiris, who's one of the first question askers from GoAQS. Something I really recommend taking a look at. Very interesting work that they're doing, looking at creating global air quality standards for everybody. So something that we can all use together, right? Because air shouldn't be something, good air shouldn't be something that's exclusive to some people. It's something that everybody deserves. No? So anyhow, but not to jump into that. So among all the panelists, are we ready to use data from low-cost monitoring in epidemiological studies? If yes, how can we eliminate their resistance? So we'll start with Tarek, then Maria, then Valentino, and then Yurgo in the same level. So Tarek, please.
Yeah, this have been also a question in my mind personally, and how to make the low-cost sensors and implement the LCM or whatever we call it. I try to say it low-cost sensors instead of low-cost monitoring. But yes, it can be applicable, bearing in mind how we handle the data, because deploying the low-cost sensors or the monitors on a larger scale and more dense network, it should give us a better information about the air quality and the exposure, and then maybe what I foresee, it will be much better than the localized monitoring stations. And if we think about the capability of having the low-cost monitoring also indoors, that improves the epidemiological analysis, because as we know, most of our time we spend it in enclosed environments like at home or schools or offices. And monitoring only outdoors gives us only the picture about the outdoor air quality and the exposure outdoor, which is less than 20% of our time that we spend outside. So basically, the epidemiology should should start thinking, or the epidemiologists should start thinking about how to implement this kind of low-cost monitoring after being calibrated and validated, of course.
Very balanced answer there. Maria, please.
Yeah, this is a very interesting question because I mean, so far, at least to the point, epidemiological studies have been requiring precise absolute concentrations at like very individual measurement points, which means reference methods. But those reference methods only attack one specific moment of time during time exposure of people being addressed or understanding what we are studying here. So I think we actually need to shift a little bit the focus to actually understand that exposure has to deal not only with the absolute value, which of course is essential to understand the real harm, but actually to be able to understand the patterns of exposure and the trends and all these temporal dynamics that we have been talking about, and that we can deal it with monitoring. And of course, I mean, I already explained low-cost monitoring with very trustworthy methodologies for understanding data and the technology. I mean, all of that is on the way, but we need to have a more global debate about what type of information we need to actually address exposure in this sense. So yes, I think we are ready. And as part of one of the players, as manufacturers, we are ready to define and work at our technology to be able to address these issues. So thanks, Sotirios, for pointing out this issue, because it's key to actually have global standards, at least global information to tackle indoor air quality and the impact of health.
So trust, I think, is the foundation that Tarek set, and you've kind of reinforced and echoed as well. I will guess that Valentino and Jurgo might follow suit, but let's see. So Valentino, what do you think? What's your take?
I think to adopt it in epidemiological studies, but we need calibrated and validated data, as Tarek already said, so we can trust the data. And with a well-designed study with focus on outdoor and indoor, I think it can be used and it will be used in the future, I think, in my opinion.
No, I couldn't agree more. I think I went to a presentation labless, for example, where everything apparently was going to be experimented in a labless lab or anyhow. But I think this very much follows suit, right? This is now with AI and these capabilities, we're going to have the ability to enhance accuracy and to enhance these studies. At least this is the future that I see. Jurgo, please.
Yes, thank you. Very good question. I would say from my perspective is that I think we are ready to use data from low-cost sensors for epidemiological assessments. So we have already indirect statistical models for assessing concentration of pathogens in rooms. So, and we actually worked with professors from Caltech on that. So there are models of 4 different diseases. What is the concentration of pathogens when an infected person has been in a room for a certain period of time, and you can detect the presence using CO2 concentration. So we have already indirect methods for that, and of course these need to be improved. These need to be enhanced and validated. But we are there, and definitely using cost-effective sensors enables us to deploy these systems at a much larger scale than what we had available previously. And even if the indirect statistical models are not 100% accurate, I mean, no models are 100% accurate, but even with like 85% accuracy, it is much better than nothing. So we actually developed a prototype during COVID times to assess COVID infection probability in indoor environments based on room occupancy levels. But I'm going to stop here. So I think we are ready. I think the methods exist, and these can be developed further. Thanks.
No, very compelling and strong points with some real life case examples there. So I would say the answer, Sotiris, was a resounding yes, with a foundation of trust, a very strong foundation of trust. Sally S., who was actually one of our panelists at the last EDIAQI webinar, and this is to anybody, but maybe we should do to all. Do you have a timeline when we moved from raw IAQ data analysis and explanations, understandably to experts, towards IAQ information translated to lay people and used in the market? From facility managers, say, customers and employees of a commercial building, instead of raw data, understandably only for us, is equal to, so is the air quality in the venue is safe, and in what ways? So basically, this really touches on this data, for me, on this data visualization. Since Yorgo has raised his hand, we're going to start with Yorgo, and maybe we can do a reverse lineup. So we go Yorgo, Valentino, Maria, Tarek.
I'll try to be quick again. So I mean, it is now. So also in the context of EDIAQI, we validated user dashboards that show whether there are issues with air quality or whether there are potential health threats in a room. So we have already like a traffic light based dashboards where the user does not need to interpret the raw data, but where just the assessment is given to them. And of course, we are happy to share this information also with others. Thanks.
Thank you for being very concise. Valentino?
I will be also quick. Regarding the timeline, yeah, it's already here. We have also developed a simulation tool in our EDIAQI project where we use the data on CO2 levels, ventilation, and people occupants, and it can give assessment based on the number of people indoors, how much you ventilate. It give you the estimate if you're living in a really good, healthy environment, or you need to improve your ventilation or buy a filter or where to put the filter exactly. And yeah, I think it's already done when we don't need to look at the data, just the dashboards, and the data will be presented to us.
Very concise and very strong actual example. So do reach out to us, Sally. Yes. Maria, please.
Yes, I totally agree. I mean, this transition is already happening. I mean, for a long time, indoor quality monitoring focused on raw data and expert interpretation. Yeah, concentration, time, calibration details, whatever. But we are seeing now this shift towards translation layers. I mean, it's not replacing data, but yeah, it's adding meaning on top of it. And this includes indicators. This includes thresholds, trends, of course. And also very interesting context-aware messages that are going to help understand if the space is performing as expected or if there's something that has changed. And you were addressing the question, the facility managers, and I think it's already underway. I mean, they don't need raw PPMs, or say at some point, raw data all the time. They just need to know when action is required, why, and with what levels of confidence. And that's our work. And I'm really proud of the work by translating data into useful information in the work we are doing in ENVIA, because it's helping actually implement action very easy without knowing anything about indoor air quality. And that is also going to help a lot for building occupants and employees, because maybe this shift is a little bit more recent or maybe even more sensitive. And here, I just want to point out one little risk of oversimplification information about indoor air quality. Of course, saying the air is safe is something the end user is going to understand, but we need to be very precise with our explanation, with translating scientific data into useful information, because we actually need to make sure everything is covered, to trust again the data, and to be able to shift from just single parameters to global air quality. So yeah, it's important. It's already there, and yeah, it's been explained before, but just taking care of oversimplification for end users, to have that in mind.
Thank you so much, Maria, because you're really doing some great marketing for the next webinar that we'll be doing, which is on data visualization. And actually, we'll take a look at this argument between simplification and complexity. And I think Yorgo's point was really interesting. Simple. So there's really a balance to be struck here. But we'll talk more about this at the next webinar. So I'll be sharing the link. Please do join. Tarek, please.
Yes, this is very important for the end user specifically, and I think the dashboard should be with different versions for the end user to choose, like something about detailed or simple. Then the user can have the opportunity to get the recommendations or the awareness hints directly in an easy and quick way. But if the user is interested about more details, it should be given to the user and look and dig and understand more about indoor air quality. It should not stop at the simplest way, but it should go beyond that if the user demands for that. That's my point of view.
I think it's very good. The context of the user. We've really done, I think, all directions with the user. I think it's a very important thing. What does the user need? Maybe that's maybe one of the biggest questions there. We have 2 more questions. Well, we have 3. So I ask you guys to be really swift with all of these. Okay, maybe we can select people for select questions. What do you think? Raise your hands, okay, if you feel like you feel strong to answer this question. Who is the person that typically cares the most? And this is from Mai Yang. Who is the person that typically cares the most about indoor air quality in a building environment? For example, facility managers or sustainability managers. And there's a bit of a second question there. Are the building management system vendors generally open to allowing third-party EDIAQI monitoring providers to integrate AI models into their systems? Yorgo, please, if you could do 1 and then Maria 2.
I'll be really quick. Yes. So sorry. So I would say that unfortunately, in case of most buildings, people are not educated enough to ask for air quality data. So we need to educate the market. We need to teach them what is important and why is it important. But I would say that the facility manager is maybe not the person, but oftentimes it's actually the HR who is interested in that. And we have multiple cases where the HR is actually has ordered these services and is looking at these data that is being collected on indoor air quality. So as I understand, I can only do 1 question.
You can do 2. You can do, but very quickly because you're very concise.
No, but maybe Maria can add on to that then. So
Okay.
I would say that the BMS vendors generally do not accept third-party sensors at all into their systems. So it's actually more about the HVAC design. What is demanded by the HVAC design, and it's a very complex topic. So it's we could spend hours on that. I'll shut up now on this.
No, thank you. We can actually also send maybe some more comments with the email to everybody with the presentations as well. Maria, please.
Yeah, just really quick, and adding to what you just mentioned, is that first, indoor air quality sits in, I think, in the intersection between operations, sustainability, and health, and that is exactly why translating this data into information, it is so important. And I agree with how different stakeholders may see it. So, and in this case, BMS vendors, they're open, I think, to third-party indoor quality integrations, but they are so far, as far as I know, they're more cautious when it comes to integration with external AI models. I think we're still in a very initial phase for AI models, but yeah, most BMS platforms support today data integrations through APIs, standard protocols, and they're used to ingesting the indoor quality data or alarms or indicators, even though maybe they don't have the knowledge or the scientific knowledge background for it. But that's on our side to actually define pretty well what type of information we are going to be sending to the BMS. So I think we're all stakeholders of the same issue.
I think we're building on some points, yeah, making really strong foundations with the users. Okay, this one I'm addressing to Tarek and Valentino because it is EDIAQI science and research, is very much academic and lab discipline. How do you think AI changes in this approach? And he uses an example. I recently used an NAN workflow automation and fed IoT indoor-outdoor meteorological APIs, then trained 5 LLM agents to interpret scientific data on HVAC engineering and air quality. As a result, I created surprising accurate IAQ analytics forecasting models. It cost 30 euros and 3 days of my work. Reactions to that, Tarek and Valentino? Tarek first.
Yeah, this is extremely interesting, but I do not agree with the first statement. Indoor air quality science and research is very much an academic, because if you think about occupants in homes, they are getting more and more aware about air quality, and they demand some answers, and they go forward to buy air purifiers to improve their indoor air quality. But the problem is they feel there is a problem, but they don't know how much serious is this problem. Do they need really an air purifier, or can the problem be solved with just simple practices in their indoor home or indoor air cleaning system or whatever they have already installed in the building? So this is good that with some combination of APIs and training and getting feedbacks provide this. And I think as an end user, they can practice this and they can improve their indoor air quality significantly. It's not a big thing or requires very advanced science to do that.
So something maybe it's citizens at a citizen level with enough knowledge could maybe as well. And I do agree very much with the point as well that I think people are becoming much more evident. I mean, the market for filtration sensors is growing and growing all the time, right? Valentino, please, but very quick and very concise.
Tarek, there's a huge raise in the issue of indoor air quality, even the outdoor. Based in Croatia, or think when looking in Zagreb, I see more and more articles on air quality. So yeah, I think this is a good example of people can do, but it will not give the exact answer to why is it like this or how to exactly improve it without the knowledge or the sensor data of their device, or of their, sorry, and home.
I think going back to the users here again, Valentino, thank you for closing today with the last question there. We have one more from Katerina. I'm so sorry we've run out of time, but we will answer that question and send it to you to all in the message afterwards. So please, we've talked about a lot about data visualization out of thin air. Making IAQ data make sense will be our next webinar. We will have our colleagues from our partners from DEDA, who created the EDIAQI dashboard to use that as a demo. We'll also hopefully have Sotirius, if he has time, who's got great expertise in terms of data visualization. And we're actually looking for some more speakers as well. So if interested, please do reach out here. Now I would like to ask you, we encourage you to become a part of our vibrant community by joining who've taken up the legacy from us, the NextAire project, the EDIAQI project, and the broader Ideal Cluster community for various, along with various other initiatives. For seamless updates and information, please scan. There's going to be lots of QR codes. I hope you have your phones ready. Display to follow the LinkedIn pages. This is the LinkedIn page of NextAire. I do strongly recommend you follow it. I will share in the chat again the InBiot. Well, I'll just actually reply to the message here of where I sent it, or copy it again from here. Yeah, I copy it again from here. So please do join. Here's the Ideal Cluster, and for EDIAQI, you have a million different QR codes. So you choose. You like X, you like LinkedIn, you like YouTube, we have all the socials there for you. We extend a really big heartfelt gratitude to our exceptionist panelists today for their really invaluable perspectives. And of course, to you, our audience, for the engaging discussions that brought this event to life. With that, we conclude today's session. Until next time, stay connected and informed. And of course, wishing you all excellent air quality both outdoors and indoors. Thank you and goodbye, everyone.